Quantum computers can finish calculations in minutes that would take our best supercomputers billions of years. But this isn't true in general, just for some specific tasks. Exactly those where we have found an efficient quantum algorithm. Alright, you want specific? You get specific. So in this video, I will discuss the four most relevant quantum algorithms that we know today. These are literally the reason why we want quantum computers in the first place. Alright, you can think of it like this. This is the 1946 ENIAC computer. It's a horse-drawn carriage. This is the 1984 Apple Macintosh. It's a car. It can do the same things as a carriage, but faster. This is the 2024 Google Willow quantum computer. It isn't a faster car, it's an airplane. It can do things that cars never could, but also planes haven't just replaced cars. And yes, they can be faster, and yes, they can be better, but only at specific things. They're absolutely great for flying to another country, for example, but they absolutely suck at getting you from home to work. And the same is true for quantum computers. The quantum hardware by itself isn't intrinsically faster or better, actually. Instead, quantum computers use a different architecture, a different rule set for computing, and this has both advantages and drawbacks. The biggest advantage of quantum computers is that they can process a lot of inputs at the same time. But their biggest drawback is that they cannot output all these results, just a single random one. And this is an inherent feature of quantum mechanics that you just can't get around. So many quantum algorithms work by increasing the amplitude of the desired output, so that when you make the measurement, in all likelihood you'll get the right one. I will now go through the most important quantum algorithms, what they do, how they do it, and why that is significant. I will only be able to give you a brief summary of how they work, but I'm looking forward to making longer and more detailed videos about each algorithm in future. Shor's algorithm is a big one, simply because of its potential impact. It can potentially break most current encryption protocols. This includes HTTPS server identification, secure email, and basically every login system everywhere ever. So yeah, a big deal. It has many parts and it uses a lot of number theory, so lots of math and none of it is really trivial. So what I will give you here is just a short summary. To understand how it can break encryption, let's look at how public key encryption works. One person, Alice, creates a secret private key and uses this to create a public key that can be sent out freely and read by everyone. If another person, Bob, wants to encrypt a secret message, he can use the public key to do that and send the encoded message to Alice. Alice can then use her private key to decode the message. And for this to work, the secret private key must be contained in the public key, but it must be extremely difficult or even impossible to figure out exactly how. One common example is the RSA family of codes, where the private key is two prime numbers and the public key is both these numbers multiplied. For example, the public key could be 15, and you would have to figure out that the two prime factors are 3 and 5. This is of course simple for small numbers like 15, but for numbers with hundreds of digits, this would take thousands of years to compute, or even longer. And this is where Shor's algorithm comes in, because it can efficiently solve prime factorization. Meaning it can figure out which two prime numbers were multiplied to obtain a larger number. And this is an exponential speedup over any known classical algorithm. So a quantum computer doesn't need thousands of years to crack it, but very reasonable timescales, more like hours or days. Shor's algorithm works by solving the equivalent mathematical problem of period finding. We already know the public key, so we know which number we have to factorize. We start with a quantum state made up of all candidate numbers, and we run the quantum Fourier transform a couple of times on this entire register. So the probability distribution for different numbers will look like this. Note that what we're interested in here isn't the numbers themselves, but the period between them. And there is a way to measure that and to calculate the prime factors from this period. Reading everybody's emails is of course very interesting to a number of people, but it will require a fully error-correcting quantum computer with at least 1,000,000 qubits to run Shor's algo in any meaningful way. And from today's perspective, this is at least a decade or two away. Also, there are already alternative encryption schemes that will not be vulnerable to Shor's algorithm. And once these are implemented, quantum computers will not be able to break anything anymore. Grover's search algorithm is the second most important quantum algorithm we know today. It only supplies a quadratic speedup and not an exponential one, but it has a much wider applicability. Quadratic speedup roughly means that when Grover manages to perform a task in 10 time steps, the best classical algorithm will take 100, and so on. It is most often described as an algorithm for searching an unstructured database. This is correct, but more precisely, the basis for Grover is a so-called oracle, a simple function that takes an input and then outputs yes or no, depending on whether the input fulfills certain criteria or not. We create an oracle function that does nothing to wrong inputs, but flips the sign of the correct input. Then, we create an equal superposition of all input states, and when we put this into the oracle, the single correct state will be flipped, but nothing else happens. This flipping will reduce the average amplitude, and the second step of the algorithm can be visualized as mirroring every state along this new average. Combined, this means the single correct state is being amplified while every other state is reduced. In the end, you want to increase the likelihood to measure the correct state so much that this is what you will get when you finally perform the measurement. And this amplitude amplification method can be used to find out a single desired element out of a large number of states. Grover is practically a quantum algorithm to find a needle in a haystack. This means it can also solve a lot of other problems where it can do a simple yes-no check. Like, for example, brute forcing a password search. Or any number of guess and check problems. Quantum phase estimation is another promising algorithm that is used as a subroutine in many applications. In quantum simulations of chemical processes or in Monte Carlo simulations for risk analysis. And it's also part of Shor's algorithm and the HHL algorithm, which is up next. The exact speedup of QPE depends a lot on definitions. If you compare it to a brute force classical equation solving, it is exponentially faster. But if you use more realistic settings and take more factors into account, it still has advantages, but nowhere near exponential. An operator acting on a quantum state will in general change this state. One important class is called unitary operators, which do not change the length or norm of a quantum state. For example, all quantum gates used in quantum computing must be unitary. A unitary operator acting on a specific state called eigenstate does not change it, but only adds a phase phi. And what QPE does is it gives you an approximation for this exact phase. I know, all of this sounds very technical, because it is. Just take my word that all of these things actually do occur quite a bit in quantum computing, so all of this is relevant. The algorithm requires such an eigenstate psi and also an auxiliary register of additional qubits. Basically, the more digits you want to approximate, the more additional qubits you need. All of these conditional U-gates basically give a phase kickback to the auxiliary qubits, and when you finally perform an inverse quantum Fourier transform on all of them together, these kickbacks are converted to the digits of the phase. The Harrow-Hasidim-Lloyd or HHL algorithm can help with solving large systems of linear equations. Linear equation systems are somewhat ubiquitous in many technical applications, like in numerical solutions for differential equations. And this might again sound somewhat esoteric, but for example, most of modern engineering is based on these tools. For example, the finite element method or FEM. Plus, it is also a major part in machine learning algorithms. Let's be precise here though, because while HHL technically does produce a solution vector for a linear equation system, this is a quantum state. We cannot simply read out all the solutions. If we were to straight up measure it, we would get only one random solution, and if we had to do this over and over and over again to get at all the solutions, this would completely destroy any speedup the algorithm initially gave us. So that's not the way. So this algorithm cannot just give us all the results. But we can use it for calculating global properties of the equation system. For example, an expectation value or a regression quantity or some statistical predictors. And this means that HHL alone cannot be used to solve the equation system, but it can be used to make solving it easier or faster. And this is actually a really good example of both the advantages and the shortcomings of quantum computing. Alright, this was the overview of the most relevant quantum algorithms that we know today. Some of them are really impressive, especially Shor, but let's be honest. This portfolio of algorithms might be a bit thin. Meaning we don't really know that many quantum algorithms which are actually useful under practical conditions. Sure, there is still a chance that we can figure out more once we have more powerful quantum computers and many more people can play around with them. But for the time being, quantum computers look set to be in a supporting role for a few select applications, very similar to supercomputers today. I mean, being able to solve all of chemistry would have a huge impact, but technically it would still be a narrow application. Well, people also don't complain that aircraft can't do everything that cars do, just better. So if you think about quantum computers like this, you won't fall easy prey to exaggerations and hype. I'm Chris and this is Physics But Awesome. At the moment, I mostly do stuff on quantum computing, quantum mechanics and cosmology. So if you liked this video, subscribe for more.